Okay. Do you see my screen? I think it is showing up.
Yes.
Okay. Okay. So today's problem is actually quite simple, quite not straightforward, depending on how you look at it. Given a root of a binary search tree and an integer k, return the k smallest value of all the value in the node of the tree. So this is a problem. To explain it, we need to understand first, because there is two key to understand from him. Given the root of a binary search tree, and of course I did not know how to use it. Okay. Let's make it smaller. Okay. Binary search tree. So just a quick recap. Binary search tree. You see this? This is basically what the value of the parent has to be bigger than the value of the left child, but smaller than the value of the right child. It's already sorted in a way. A binary search tree will always be sorted in this specific way. So we have here a binary search tree that started, the root is 3, and the left child is 2, the right child is 4, and then we have the 1. It doesn't have a left child, but the 2 is bigger than the 1, so the child, it will be a right child, not a left child. In the binary search tree below, it started from a 5 as the root. We have 6. 6 will go to the right because it's bigger than 5. We have 3. 3 is smaller than 5, so it will be on the left. And then we have this subtree. This subtree will have 3, and the child of it, the left child, will be 2 because 2 is smaller than the 3. We have the right subchild will be 4 because 4 is larger than 3. 2 will only have the left subchild, the left child, which will be the left child because its value is less than the 2. That's basically the and binary search tree cannot have duplicates, so it's basically binary search tree. The other thing is return an integer k. Return an integer k. They will give us an integer k. Return the k smallest value. K will start from 1, 2, 3, 4, whatever it may be. So they if they want the smallest value, so the k will be 1. The smallest value will be always the leftmost child. Simple enough. But the problem is they are not always asking for the smallest value. Sometimes they ask for the second smallest value. In this case, it will be 2. The third smallest value, in this case, it will be 4. The fourth smallest value, I cannot go up, but I have to go to the right side, and that's the bit of trick on it. So it depends on what smallest value they want. What smallest values they want. So it depends on the value of the key. Very simple, very straightforward. Any problem in understanding? Thanks. Welcome. Okay, we have that in us. Okay. Did everyone understand the problem? And complete silence in here.
It is. It is.
Come on, people. Anything. And the answer should be yes. Just something in the comment, please. Type yes, of course, is a wrong. Yes, thank you. Thank you. Now we have at least 2 people, so I'm not doing myself. Okay. So let's start writing some value here. Let's say I will say this is okay, that is definitely there. I will start let's make it simple. I will take this one. Can I copy it? I have no idea. Can I copy it and just put it here? Apparently I can. Good. So this is what we have so far. So how do I do it? I will like to play a game. Let's make it do the dumb thing first, then trick people into thinking you're actually smart. So we will do this in two approach. The complete straightforward approach is a very dumb approach, and it will work. And then we will make it look a bit smarter for if you wanna like make it look like you understand what you're doing. So yeah, it will take about 5 minutes in either solution. So let's go. First of all, I'm thinking. Well, the first thing I'm thinking of using an array. How do I get an array? Because you already have it like in they already like use it to express the element of. So what I'm thinking is just uh I will have an array and I will loop through the nodes. So this is like the simplest solution. First solution I think about when I think about this. I will need to know. I will keep the element of the array, but I will start appending when I like. I will pop. I will keep an element in the array, and then I will take the element of the array. So basically, I will just let's say I will initialize an array. Let's call it stack. Will be an empty array, and then I will have a counter to know uh, where did I reach the smallest element, yes or not yet. The k element, yes or not yet. And then I will let's say just say I don't think I need it, but let's just give the node which will start to be the root. Then I will loop. So while node or stack. While I have element, I will do another while node while I have node. I think I will just take it up there and I will keep this one below. Keep it because it will explain in a minute. Okay. Am I think of it. So I will say stack dot. I will append the node uh, the node, and then I will go left. So because when I keep going left to get the smaller value. So just I'm here, okay. I will get node equal node dot left. So I keep going left. I will start from the root. Then I will append the node to the stack. Then so the first value of the stack, let's just put it here. Let's say the stack will have first. Let's say it will have the 5, the element, not just the values. Then I will go to the left. Then it will have the 3. Then I will go to the left. Then it will have the 2. Then I will go to the left. Then it will have the 1. It doesn't have anywhere else to go. So I exit this while loop. Once I leave this while loop, I will take the 1 and then So I will say node equal stack dot pop. So basically in here the node will be the one, and I will remove the one from here. Now it's while node does I will have to ask if node does not does n I will that's where I will the counter will come in handy, because I will increase the counter by 1. This is the first time I popped the first element I popped, so I will have to ask if n equal k. Is n is the target? In this case we have k equals 3. I forgot to actually say that k equals 3. Is k equals target? No. But if k, so I will leave this condition for now, empty for now. Just basically, if k equals target, I will return the node value. But we're not there yet. So I went right. So it right wasn't. So I will go node equal node dot right. So is there a right? It doesn't have a right. Then I will use the one does not have a right, because if you remember node now equal 1. The one does not have any right. So I will go back. I won't enter this while loop. So node will equal stack dot bob. So I will back into stack, and the node now will be equal to the 2, and I will bob the 2 from the stack. So again, does n equal the k? I will increase the n by 1, so n equal 2. And I ask the question, if n equals k, n is still less than the k, so then I will not go there. Then I will go to the right. Do I have a right node? No, I don't have a right node, so I will not enter the while loop. Then I will change node dot stack. So now the node equals 3. Equals 3. The n will increase by 1, so the n will be 3. And I will access if n equal k. Yes, in this case, k was equals 3, so the n equals 3. I will return noted value. Yes, it's correct. And I don't need. What about if n was equal in 4? It's not 3, 4. So if n equal 4 and I am at 3, so I don't enter this if conditions. Then not equal not to right. In this case, not equal the 4. And I enter this while loop. Do I have? Do I have a right? Yes, I have a right. In this case, I will add to the stack the node, which in this case is the 4. Am I? Come on, where is which is in this case I add the 4 to the stack, and I go node to left. Do I have a left here? No, I don't have any left. Then I will go node stacked bob. I will bob the 4, and the node now equal 4. Then increase the n by 1, so the n is 4. Is n equal k? Yes, n equal 4 and k equal 4. Then I return the value, and it will give us, it will work. Do you have problem understand it? Or is this dumb solution clear enough? Any answer, please, someone? Okay. All right. Makes sense. Did not make sense, but it's good. Let's just try it and see if. Okay. No, not this. Okay. No. Yeah. No, okay. 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 I will have to do it manually. So yeah, no, it's here. It's I believe it's here.
Manna,
Let's
somebody
try
is
it.
asking you to zoom in a little bit, if you could.
Syntax error. What is the syntax error? Oh, the if. It's need. I did not hear anything that was saying.
I said somebody is asking you to zoom in a little bit, if you could.
How can I what?
Zoom in on the code.
Oh, okay. I will. Oh. That is definitely happened. Again, what? Oh my god. Let's. Am I right in it right? Or and again, Bob will give me a runtime error. I believe that's good. And it passes. Completely fine. Simple solution, like I told you. The dumb solution, the first thing that come to your mind, and it's not bad, not great, not bad. Is there a way to make it look smart? This is a very simple, very basic solution. So, like I said, let's play the game of how do I make myself look smart. So this is a very simple solution, the very first solution that come to mind. Let's use some fancy algorithm. Basically, anyone want to guess what fancy algorithm I'm gonna use? Come on, people. That's basic. And I believe just left. Come on. Anyone want to guess? Anyone? I will use recursion. Anyway, that was very disappointing. But okay, I have no idea how to do this. No. Oh, we will use. I'll use recursion, which is basically just replace the while loop. So in recursion, I will use recursion and queue actually. In this case, let's make it the stack will equal the queue. And let's write the recursive function, which will say def. Let's call it order. And then I will give it the node. And then I will say order. Node dot left. I'm going left. Then I will say stack dot append node dot value. And then order node dot right. I think that's it. I don't need anything else. This is a recursion function. It will go left unless there is no left. Then it will go. It will append the stack and it will go right. And then I will call it and I will give it the root. Then I will return. Oh, let's try it. Come on. Then right. here and should work. Yes, it worked just fine. Let's submit it. It's actually faster, but this is not dependable. But it looks better than the wild one. But for me, I will always prefer the wild one first. And that okay. Uh, I will let you take this one, Sabah.
And I will kindly skip it. Thank you.
Okay.
All right. That was nice. I actually like the recursion one better. It looked cleaner.
The recursion.
Yes.
Yeah, I know. That's why I said it looks smarter. That's why I put it. That's the game I wanted to play. How to make yourself look smarter.
And it did. It did.
Okay.
All right.
So how to trick people into thinking you're smart.
Okay.
Now I will take the Backman question.
I will kindly skip it. Thank you. I
Okay.
do not deal with time and space complexities. Pacman, if you
Okay.
would be so kind as to do it yourself, we would really appreciate it.
Yes. You are a developer yourself. Come on.
No, like, I feel like they're the same. That's why I was asking because the previous one was populating a stack with the entire array, with the entire binary tree content, and the second one was doing the same thing but only using recursion. So I was kind of wondering whether there would be any improvement, really.
Actually, like, for me, the way I think about it, I like the first one because I don't have to go this one. I will have to go through the entire thing first.
Yeah,
Like, for me, I'm thinking this will take longer because I will have to use the entire. But the first one I don't, because if you remember, I will stop once I reach the key smallest element.
yeah,
I will not keep bobbing, but I will only like go through the half the array first, which is the left half, and I will go to the right one by one. Yeah, I will go to all the left, and then I will start to go through the right one by one. So
yeah. But like,
in
exactly.
my brain, the way I thought the first one would have been better, but I apparently it's this one is faster. Maybe because I
Mm,
used a TQ here, but the first one I used normal stack, a normal array. But in my head, I there is not a lot of difference actually between the two of them.
yeah, like worst case, they're probably gonna be the same because the worst of the worst, even the other one, they still have to populate the
Yeah,
stack
because if
with
if
the
k
entire
if
tree
k is
content.
equals the same, the length of the array, then you want the
Yeah.
highest, not the lowest. That's yeah. I don't see much difference in both, but
Okay,
this one
thank
looks
you.
smart.
Okay, nice one. Nice going.
Okay,
I'm happy.
thank you, Beckman.
Thank you, Chief.
And back to you now, Sabah.
Okay. I will start sharing.
I will. I need to stop this. Uh, Shikara is here. I sorry for butchering your name. Bernice, that's my job today.
Is my is my screen clear?
Yes.
Is my voice clear?
Yes.
Great. Okay. We're gonna try to solve this word search. Given an MXN grid of character board, so we have a board, right? And we have a string word. We return true if word exists in the grid. So it's like the game that we can play. You have a board, you have a like a series of words. In this case, we only have one string. I can hear my echo. Um, if anybody could mute their mics. Okay.
I don't hear anything. It's good.
Okay. So the game that we have like boards and then words, and you look for the word inside of this board, right? In this case, we're only given one string, and we only return true if the word exists, and false if the word doesn't. and the word can be constructed from letters of sequentially adjacent cells. So you can go right, left, up, and down. You cannot go
Sabah,
diagonally.
someone cannot see your screen, but I can see it. Is anyone else have problem seeing Sabah's screen? Okay, then Stanhope, maybe you can try. Okay, Stanhope, maybe you can try to exit and then join again.
Okay, I will continue until he.
Did you switch from the previous stream that Mennatalla was sharing? You need to switch from that one to
I actually
the new
closed
one from
mine.
Sabah.
I closed mine. Okay, she's back. Can you see it now, Stanhope? Stanhope, can you see the screen now? She has gone quiet. I don't know if it's he or she, but yeah. Okay, you're good,
I
Sabah.
assume it's a he. Okay. Um, yeah, the word can be constructed from letters of adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter may not be used more than once. So the letters can be like adjacent vertically and horizontally, but not diagonally, and you cannot be using the same letter or the same cell twice. So in this case, for example, ABCC, you cannot use the same cell twice. In this case, we have the word or the letter is the string of letters is A, B, C, C, E, D, and then we have that inside our cell. The other example is C, and we also have that, so it might not always start from the beginning. It could start from the middle of the cell, of the board, right? Again, you cannot use the same letter twice. For example, in this case, you have a S here, you have an S here. You could start with this one, but you don't have any E's neighboring, so you would give up on this side of the board, and then this one you have an E up top and E at the bottom, but you cannot use this twice. So you'd give up on this side of the board and you go down S E and E, and you would get the word C. The third example is you have ABCB, right? And you have an A here, you have an A here, but this one doesn't neighbor any B's, so you give up on this one, and you have a B and then a C, and a B again, which again you cannot be using the same cell twice, so you cannot go back and use a B. So the letter or the word ABCB doesn't exist in our board. It's pretty straightforward, right? Let's copy it here. And we could, I believe, use both the BFS and DFS. I'm not sure DFS or like backtracking. Yeah, that's the word. We will be using backtracking today because basically you're starting at different points of the board and you have different paths that your word can take, that the potential word can take. And as you keep going, if any path doesn't work out, you just give up on that path and you go back to a different path. This one doesn't show it, but this one does. So let's put it here, right? So in the first yeah, in the first you would start with this one. Okay. Let's get some red, kind of paste it in. Okay, you have two S's, right? Because the word is C, right? You have two starts of the word, right? And so you have two potential paths, right? This path you would look for the second letter. You have no letter vertically, you have no same letter horizontally, so this path you give up on it, right? And then you follow the second path, the green path, right? So now the green path, you have an SE up top and you have an SE at the bottom. So now you have two paths again. So you explore these two paths independently. Now backtracking is when you go here and then you have no other E's. So you give up on this path and you backtrack your steps into, again, the S, and then you go follow the second path. The second path will lead you to the second, the second, the first E, and then the second E, and then this one you would take as your true to return, right? If you have found no paths, then you return false. Is the question clear? Is the problem clear? Yes. Okay. Great. As I said, we will be using backtracking. All right. Backtracking would be just like a recursion. We would have a function backtrack that it will allow us to explore each cell individually, right? So this backtracking function will have like different, will be given different indexes, right? So x equals 1, y equals 0, for example, for this one, right? Or y equals 1, x equals 0. And it will explore the neighboring cells. So this function will have, for example, we can have the directions, right? And it will be a list of direction we already know, like -1, 0, etc. Right? And this backtracking will loop through these directions and it will get like new coordinates, right? So for example, with this S, it will explore the the top neighbor, the right neighbor, and the bottom neighbor, and technically will also explore the left neighbor, but since it is not in limits, then it will not actually call the recursion for it. So you check first if the coordinates or the neighbors are in limit, right? You check if they are in limit. You also check if they have been checked or not, right? As I said, you cannot use the same word twice or the same cell or the same letter twice. In this case, it's very easy. You would go A, B, C, and you would look for a B, and technically you can go right, you can go down, and you can also go left. And if you go left, you would find a B. But B is already used in this particular path. Another path could get to this B and it would not be considered used, right? Because it would be the first time it would visit this B. But for this particular path, it is already visited. So you cannot go back and use a cell that you've already visited. So you need to keep track of cells that you have visited inside of your like board, but only for that specific path. As I said, another path could be used in that cell and it would not be considered visited. So you check if the neighbors are in limit and if cell has been,
Sabah, you have been cutting out for a while. You need to go back a bit.
oh, how long?
About a minute.
What's the last thing I said?
You were in the orange area
In here.
when you got cut off. Yes, you were here when you got cut off.
Okay. So I was saying that you need to first check if your neighbors are within limits, right? S will check its right neighbor, its up neighbor, its left neighbor, and its bottom neighbor, right? But this right neighbor is not within limits. So first, after going through the directions, you check if neighbors are within limits, right? But you also check if those cells or those neighbors have been checked before. So I was saying that, for example, A, B, C, B, in this case, if you go, let's take this one actually. So in this case, you could start with an A and you would go to the B and you would go to the C, but C will look for its neighbor in the right, which is an E, in the bottom, which is a C, and then on the left, which is a B. And it wants, like, because the word is A, B, C, B, right? So it would look for the B again. It would find it here, but this should not be used again. It was used the first time, it should not be used the second time within this particular path. Another path could get to this B and it would not be used. But for this particular path, it is used. So we cannot find the B again. In this case, it will return false. So we need to find a way for us to keep track of keep track of whether a cell has been visited for that track or not. So we check if the neighbors are within limits and if the cell has been visited. Now, there are many ways to check for that. You can keep an array, right? For each track, an array that would you would append the coordinates to, right? Or you can make an entire board, so an entire board of the same size, but instead of the letters, you would have like a zero. And each cell that has been visited, you mark it with one. So you know, for example, let's remove these. So you would have zero behind each, well, I guess that doesn't show, but you would have zero behind each of these letters, or instead of each of these letters. And whenever you, I guess, explore one of these cells, you would mark it with one. And then if you get back to it again, you would know that that is a one, and then you shouldn't explore it again, right? And you would do that, for example, like before exploring the neighbors, you would mark the cell, right? And then you explore the neighbors, you check the neighbors. So if the neighbors go back to the current cell, they would find it as marked. Now, as I like this idea of doing like the whole board, but as I said, you can do just like an array and keep track of the cells. So this board, you would, I guess, initialize it beforehand. So make board board of mxn. Am I still audible? Yes?
Yes.
Good, good. Okay. So you would make a board mxn with with well, initialized with 0. And in here, the current cell, you would make it as, for example, I guess like second board. And we would be given an x and a y, and you would mark this current position as visited, right? And at the end of whatever recursion that is, because here, if it is within limits, right? If it is within limits, and if the cells have not been visited, or has not been visited, then you would call a recursion on the neighbors, right? So for example, if x plus 1, then you would call the backtrack on, like backtrack, and you would pass it x plus 1, right? So for example, if x equals x plus 1, for example, and y would equal y. So in this case, we have gone right, right? And we know that this position is within the limits and the cell has not been visited. Then we call backtrack with this x plus 1 and with a y, right? Now, so I guess in here we would have an x and we would have a y. Give me a moment to plug my PC. All right. So now that we are inside of the neighbor, what should we do? We need to check whether this actual cell is in track with like our word. In this case, E. E will explore is right neighbor, which doesn't exist. So we'll not call the backtrack on that. It will explore the top neighbor. So we need a way for us to check this top neighbor, whether it matches the our like word, right? SE. And we need the index of the letter that I should check, right? So along with passing the x and y coordinates, we would also pass an index, right? The index of that cell, which letter should it correspond with, right? So now this backtrack is gonna also pass an index. And here, when we want to call the neighbors, it will be the letter plus 1, the index plus 1. For example, if we start with S and we check S, the neighbors should be checked against E. They should not be checked against S. I hope that makes sense. So the backtrack will have also an index, but it should be the following index, index plus 1. Okay? Now, once I am in that neighbor, I need to check the validity of that neighbor. So I need to check if the word index equals or matches with the cell. So I guess it's board x and y, right? So this, we check whether this word or this letter matches with our word, right? If it doesn't, then for example in this case, if we're exploring C, right, we need to check if this letter matches with our word. If it doesn't, there's no point in exploring this path because it doesn't match. So if it is not, so in this case if it doesn't equal, then we just return false. The path does not we can just give up on that because it is not correct. Now, also, if we are passing word index, if we are passing index, we need to first check the if the letter, if like the length of the letter is matching the length of where we are. For example, if I am at my third letter and I've passed this check. So this check tells me if this letter is matching the last letter of this word. If it is, then what is the next check? I need to see if the word that I've created from this path is like is done, right? So I am as S and I explore E and I explore the second E. Before exploring the neighbors, I need to check if this is the end of the path. Did I find my word, or do I still need to look for other neighbors? So you check the length of your index with the length of the index that the so you compare the index of the word that you have with the index that has been passed to this iteration of the backtrack. So if length of word is, I guess, equals to index, that means that we are at the end of the word, right? Index and length of the word, well, index is going to be minus plus 1, I believe. Then we can return true, right? This last letter matches with the last letter of the word, and the length matches. So that must be this path is the whole letter, since the lengths match and the words match, the letters match. So we return true. Does it make sense so far? Does it or does it not? If anybody has any questions, they can ask. Okay, good, glad to know. All right, now, now that we have checked the validity of the cell and we have checked if we have finished the whole word, then we mark the current cell as visited, right? We loop through the neighbors and then we check if they have been visited, if it is valid to check those neighbors, and you call the backtrack on them with the right arguments or parameters, and then you uncheck the current cell because you don't need it checked, you finished with it, and you don't want another path to have this one checked and like it has not been used, right? So at the end of your callback loop, you just mark it back as unused. Good. So this is, I believe, is our backtracking function. Now, outside of this function, we still have some stuff to do. We have made our directions, we have initialized our board, right? But we still have to call our backtracking function. So we call this function on every single cell of this board, right? We call it on A, we call it on B, we call it on C, we call it on literally every single cell of this board. Because the word could be starting from here. The word could be starting from here. We do not know. So every single cell of this board will have the backtrack called. Now there are some things you can do to minimize to make it more efficient. So as to like check whether the letter is the one starting with before you call the backtrack. We can do that. So loop through the board and then call the backtrack on each cell that matches with the first letter. So you compare with the first letter of your word. You check if S, so you go A, does it equal S? No. So this path, any path that starts with A, will not lead to anywhere because we can call it and it would return false from here. So we do not really care for, it will return false either way, whether it enters the backtracking function or not. So we can, I guess, filter it from here. You call the backtracking only on letters that match with the first letter of the word. And then if backtrack, it would, like we would pass X, we would pass Y, and we would pass the index of 0 because we're starting with the first letter S. So we start with 0, and then if it is true, so if it, oh boy, so if, what have I done? Okay, if it equals true, then we return true, right? We have found a match. Now, if we have not found a true in all of our board, that means we have not found our word, and then we return a false. Does this make sense? And there are other ways of, I guess, minimizing the time that you would spend here by just checking if, for example, the length of the word is bigger than the amount of letters that you have. For example, say you have a 1 by 3. You have 3 letters in your entire board, and you have a word that is consistent of like 5 letters. It is not possible to find this 5 letter word in a 3 letter board. So you would just scrap, you return false from the very beginning. You could also check for the, I guess, the count of each letter inside the board. If one letter doesn't exist in the board, if there are many things, I believe we will get to them because they are necessary. But for now, is what I've written down clear? Is this clear? And do we start writing it in code? All right. Great. I will copy all of this. And put it here. And Manna, something you didn't, I guess, know about, you can just do this. If you select the entire text and click on the tab, it would.
Thank you for informing me of that lovely after I finished doing it manually. Thank you for very helpful.
I had fun watching. Okay, so we make a board MNX initiated with 0. So I guess it's a mirror board. It is, I guess we could just call it visited equals. And I like doing it like this. You have, I believe, or I guess, okay, before going to this, we can just write our m's and n's, right? So it would be easier without having to calculate them every time. So m, I believe, is the length of word, and n is the length of word 0. So this is the I guess length and width, the height of, and width of our board. And now this, I believe, we can just do visited equals 0 times, and I believe it would be n for range n. I could be switching them, I wouldn't know, but we will find out. So this just adds zeros times, I guess, n, right? So it's a row of zeros, and like in a loop of columns. No, it's columns, 0 columns, and then rows. So this just makes a board of zeros, basically, with the m and n that we have. All right, and here we will have our directions. I'll just not write in these again. So this just basically gives us directions: right, up, left, down, that we can add to our coordinates. So basically x minus 1 would make you go left, x plus 1 would make you go right, etc. So it's 1 0, that would make you go right, I believe. 0 minus 1 would make you go up, and 0 1 would make you go down. I believe that is it. Now the backtracking would take x, it would take y, and it would take the index. Now you check if word index doesn't exist in the board, and you return false. You check if length of word equals index plus 1, and you turn true. Now we call this visited, I believe. Now you mark this current cell as visited, right? And you loop through directions. So I believe for dx, dy, and ds, right? Now this will give us minus 1, 0, and x, y will equal x, I guess, okay, new x and new y equal x plus dx. So if we had, for example, 2, we would want 2 minus 1. So we would go back to plus 1, which would make us go forward, and y plus dy. We check if the neighbors are within limits. Now, not only if the neighbors are within limits, but if the index is within limits too, because we're passing index plus 1, right? We need to check if the list needs if the index, because we're checking it here, we need to check, okay, I'm not making much sense. We need to check if the index is within the word limit, right? 0, for example, 0, 1, 2, 3, 4, 5. We need to check if we're passing like 6 or 7 when we like that is the end of our word, because here if we don't do that, this might give us an error, right? It could be beyond the limits, and this would give us an error. So we check if the neighbors are within limits and index within limits. So if 0 is smaller or equal than our new x, which is smaller than m, and if 0 is smaller or equal than new y, which is smaller than n, right? And if index plus 1 is, I believe, smaller than the length of word. Yeah, okay, that's good. And if the cell has not been visited, so and visited new x and new y doesn't equal 1 or equals 0 or not visited. So I believe. So if the x is within limits, if the y is in limits, if the new index is within limits, and if the cell has been visited or not. Now, if all of these are like pass, or if they're true, then we call the backtrack. Now, the way this call backtrack is gonna go is backtrack, it's gonna be new x, and it's gonna be new y, and it's gonna be index plus 1. But we need to hold the results of this somehow. We need it to, if it returns false, then it should not make any change. But if it returns true, then it should change the result to true. You could either, so if the backtrack results, if it is, I guess, true, or if it's just backtrack, then you return true. If not, then at the very end of your loop, you return false. All right. Here now we are gonna have to visit it. So xy is gonna be 0. So we uncheck or unvisit the current cell, as I said. So if another path comes back and leads to it, it doesn't return as like false because the cell has not been visited by that path. Okay. And we return false. Great. Now, outside of the function, we loop through the board. So for x in m, for y in n, then we call the backtrack on each cell that matches the first letter. So instead of this, yeah, if backtrack, okay, if I guess board x, y equals word 0. So we check if this cell, the contents of the cell, matches with the first letter of word, and if the backtracking of this is true, or we just do this, then we return true, else we return false. Does anybody have any issues with this, or does anybody see any typos or something that I might have done wrong here? Is it good? Does it make sense? Oh yeah, we will see. I always mix those up, and we will see if, yeah, I guess. Oh, range. Yeah, you're right. Range. and range and okay, all right. And then if we submit, we might have a time constraint thing, or we might not. We'll see. We do not. Okay. Submit again. Thank you. I have had a higher percentage last time, which makes me think that what I've changed might have made it slower rather than faster. So what I've changed from what I did on my own was, instead of checking this, which I thought was gonna be more efficient, I just had it keep going through the loops. I'm not sure. I thought I got more like efficient. Let's see my earlier submissions. So this one basically lets the loop go through each one and uses OR to get only the true values. So result is initialized as false, and it takes the result, so the previous result, or this DFS thing, and it basically, and also, oh yeah, we didn't do this. Okay, so this one basically just checks if the current, if the words in the word exist in the board, right? So we make board as one singular string. So a string consisting of A B C E F C S A D E E, right? As a like a string, and we check letter by letter from word if that letter exists inside our our string. And if it doesn't, then you can return false from the very beginning. We can do that. So if our board string equals, so you join the rows, the columns, I guess. Yeah, you join the rows and then you join them together. Join each cell in a row and then you join the rows together. So dot join, I believe, I'm not sure how to do this, I don't remember. I guess board. So it needs to be like strings, right? So for and board, and then you put all of this inside a second join. Truth, don't remember. And then you check for this. Let's print this first. Not sure if it is actually correct. Okay. Expect a string and list found. Okay, then apparently I don't. Okay. So you join the row for row and rows, and then for row and boards, and then, okay, that doesn't make much sense, but you just check for the character inside the word, and if you don't find it inside your string, then you return false. For example, if you have A, B, C, Z, for example, inside of your word, you check if Z exists in your board. If it doesn't, then there is no point in looking for that word. The letters themselves don't exist. Let's see how much it will give us with this. Believe this should be, yeah, okay. Yeah, I think it is much faster. Oh yeah, much faster. That is in the 90s now. Okay, yeah, that is it. Hope that made sense. Why don't you? Well, why? What do you mean? I believe in Python it does work. I mean, I've used it. Oh no, it does, it does. Okay, I believe that we are done. I hope this Monsif less PLD was to your standards. Yeah. Do we shamelessly plug our website again, Minna?
Yes, yes.
Okay. All right. If you have not seen our website that Minna and I have um, developed,
Go
you should.
play with it, please.
Yeah.
Leave your project, share, and try to find all the Easter eggs. So
Yes.
far, no one actually have found a lot. Like we put a lot. We're very disappointed in you. Not a lot of Easter eggs were found yet.
So you can basically just upload your project. You can see everybody else's projects. You can upvote. You can share. You can also check people's like profiles and have like see their socials and projects they have been part of. So that's nice. I see myself. Yeah, you can
Yeah.
search by cohorts. So far, cohort 13 has dominated the fields. And yeah, looking forwards to your projects in here. You can potentially be the number one project.
Few had tried. No one has managed to do it yet.
Throne the queens. Okay, yeah.
Okay.
It was a nice session with you guys. And
We bid you good night
see you
and have a
next time.
good night. Have a good day.
Have a good night, everyone.
Goodbye.